Hello everyone, myself Rachna Bist, Assistant Professor in School of Pharmacy, BBDU Lucknow. Today's topic of lecture is cycloalkanes. So first we have to see what are the basic classification of an organic compound. If we see the organic compound, they can be classified into acyclic or open chain compounds and cyclic, or they are also known as closed chain compounds. Open chain compounds, we have seen the alkane, alkynes, all these are the open chain compounds or aliphatic compounds. And whereas in a closed chain compound, the ring is present. That's why it's known as cyclic, because of the ring. So cyclic compounds are further divided into homocyclic and heterocyclic depending upon the number of atoms. How atoms are of same type, then it will be called as homocyclic, and if the atoms are of different types like carbon, nitrogen, oxygen and sulfur and so on, so these compounds are called as heterocyclic compounds, which are further divided into alicyclic and aromatic compounds, and aromatic compounds are further divided into benzenoid and non-benzenoids. In aromatic compounds, benzenoid which contains the benzene ring, and non-benzenoid means the compounds which do not contain the benzene ring. Similar classification is in the heterocyclic compounds also. So first we will see what are the cycloalkanes. So they are also called as cycloparaffins, and are saturated hydrocarbons in which a carbon atom are joined by single covalent bond to form a ring. So cycloalkanes, they are generally saturated hydrocarbons. They do not have any double bond or triple bond. They have only single bond. That's why, and we know that in organic compounds, the compounds which are saturated are known as alkanes. They are also known as paraffins. Therefore, cycloalkanes, they are also called as cycloparaffins because of the saturation. Now the next is the molecular formula, with the general formula of the cycloalkane is similar to the alkanes, that is CnH2n. Physical properties of the cycloalkanes includes that certain cycloalkanes, they are gaseous in nature and some are liquid in nature. So the lower cycloalkanes like cyclopropane and cyclobutane, these two compounds are only gaseous in nature at ordinary temperature, whereas the other higher cycloalkanes like cyclopentane, cyclohexane, cycloheptane and so on, all these compounds, they are liquid in nature. And the melting point and boiling point of the cycloalkanes similar to the similar to the alkanes, like they increase with the increase in their molecular weight. Their density is less than water, and they are lighter than water. And being an organic compounds, they are insoluble in polar solvents like water, but are soluble in organic solvents. Next is the preparation of cycloalkanes. Cycloalkanes can be prepared from various methods. First one is the Freon's method, which is a dehalogenation reaction. Here the this is suitable dihalogen compounds. So they are treated with the sodium or zinc at a very high temperature. Then dehalogenation will occur, means removal of the halogen group will occur, and formation of a cyclic compound will be there. So from this reaction you can see that 1,3-dibromopropane, it has two atoms of bromine in its compound. On reacting with zinc or sodium at very high temperature, the bromine will get removed by the zinc, forming ZnBr2, and a ring, or this is a cyclic structure of cyclopropane is formed. Similarly, in 1,4-dibromobutane also, the two bromine molecules are removed by zinc as ZnBr2, and a cyclic compound of cyclobutane is formed. Next method of preparation is Dickman condensation reaction. Here the condensation will occur in these type of reaction. Only diesters are used, which are treated with the sodium, because of which an acetoacetic ester will be formed, and beta ketoesters are formed due to the condensation. These beta ketoesters they will again get hydrolyzed to form cyclic ketones, and these cycloketones on reduction, or if they are undergoing Clemmensen reduction, they will form a cycloalkane product. Next preparation is from pyrolysis of dicarboxylic acid, which can be calcium or barium salt of the adipic acid, palmalic acid, or subbaric acid. All these are salts are heated at a very high temperature, and then they will form a beta ketone, which will undergo the Clemmensen reduction reaction to form cycloalkane compound. Next, fourth reaction is 2 plus 2 cycloaddition reaction. It is an addition reaction which occurs in the presence of UV rays. Here, two molecules of ethene will undergo the addition reaction, forming a cyclobutane product. Whereas in disulfide reaction, here also one diene is required and dienophile, which are the requirements of the disulfide reaction. So on reacting at a very high temperature, it will yield cyclohexene by the transfer of bonds from diene to dienophile. Next preparation is from Simons-Smith reaction. Here the alkene is treated with iodomethane in the presence of zinc copper, which will result in the formation of cyclopropene and Zn-I2. We can prepare cycloalkane from benzene also by their reduction, or you can say by their hydrogenation in the presence of a nickel catalyst and at a very high temperature. As you can see from this reaction, the benzene undergoes hydrogenation or reduction, forming an cyclohexane. Similarly, toluene is also reduced to methyl cyclohexane. Next preparation is by Clemmensen's reduction reaction. Here the condition is in the presence of zinc mercury amalgam and concentrated HCl. The ketone group is reduced and removed in the form of water, resulting in the formation of a cycloalkane compound, that is cyclohexane. In Wolff-Kishner reduction, it is also a reduction reaction, but here the condition is different. Here hydrazine NH2 NH2 is used in the presence of a base and glycol to form a product cycloalkane. Next are the chemical reactions of the cycloalkane. Here the chemical reaction of the cycloalkane is due to the cyclic nature. As cycloalkanes, here all the carbon atoms they are sp3 hybridized. sp3 hybridized, why? Because all the carbons they are saturated, a single bond. But that's why we say that they are similar to alkane. But they differ from the alkane in one respect, which is that they are highly reactive. Means the cycloalkanes they are highly reactive. Like the lower cycloalkanes they are very unstable and highly reactive, whereas the higher cycloalkanes like cyclopentane and heptane and so on, all these compounds they are stable and are unreactive. So first chemical reaction is a free radical reaction. Here the lower cycloalkane is treated with the chlorine in the presence of UV rays and at a very high temperature, then it will reduct in addition product. So here we can say that here it's a molecular substitute. The chlorine is hydrogen is substituted with the chlorine. So here the product will be formed chlorocyclopropane and bromocyclobutane. Substitution reaction will occur. Next, in addition reaction, the two types of reaction can occur. First by the addition of halogens and second by addition of the halogen acids. First by addition of halogen, here the breakage of bond will occur during addition process. So bond will break from any two carbon between any two carbon, and the bromine molecules they are added at both the end of the carbon. As we can see from this reaction from cyclopropene, and the bond will be cleaved between two carbon, and so the chain will be formed of CH2 CH2 CH2, and then bromine, two molecules of bromine they can add on both the ends of the carbon to form a 1,3-dibromopropane. And similarly, the cyclobutane also, the product formed, the chlorine molecules are added at both the ends of the carbon and forming a product 1,4-dichlorobutane. In addition to the halogen acids, Again, similarly, the cyclic ring will get cleaved between two carbon and forming product where the hydrogen will be added to one end of the carbon and bromine molecule will be added at another end of the carbon, forming the products 1,3-bromopropane in case of cyclopropane and 1-chloropropane in case of cyclobutane. So these are the important reactions of the addition reaction, which will be shown by the lower cycloalkanes like cyclopropane and cyclobutane only. The higher cycloalkanes will not give such reactions because they are highly stable and thus are unreactive. Next is the addition of hydrogen. Here the reduction will occur in the presence of a nickel catalyst, where again the cleavage will occur and hydrogen will be added at both the end of the carbon to form an alkane like propane and butane. Now, the next topic of of the cycloalkane is the stability of the cycloalkanes. So, this is the very important topic in which the stability of certain cycloalkanes are described by some of the scientists, like Bayes strain theory, Colson-Moffat theory, and Sasse-Moore theory. So, all these three theories are based on the stability of the cycloalkanes. So, first stability is given by Bayes' strain theory, which says that the main postulates of the theory are in cycloalkanes, each carbon atom is sp3 hybridized and bonded to other four carbon atoms. We all know that the cycloalkanes they are saturated compounds and so they are sp3 hybridized. The angle between any four adjacent bonds should be tetrahedral. Now this is the point. It was according to the Bayer, it was given that the bond angle between the two atoms, between the two carbon atoms, it should be 109.5 degree. The cycloalkanes are planar due to cyclic nature. As a result, bond angles between adjacent carbon atoms in the ring are not longer equal to the normal tetrahedral angle. The angle deviation varies with the size of the ring. So here we can say that the cycloalkanes being planar in nature, it is not necessary that their bond angle will be 109.5 degree. It can be less than 1.109 degree or more than 109 degree. And because of this deviation from the tetrahedral angle, the instability is developed in the cycloalkanes. And this angle deviation it will vary if the size of the ring varies. Third point which the base study gave was any distortion or deviation from the normal tetrahedral angle causes strain in the ring and produce instability to the resultant molecule. This strain is known as angle strain. That means that if a molecule, or you can say if a bond angle between two carbon atom in a cycloalkane is less than 109.5 degree or is more than this angle, then it will cause a certain strain, means a certain stress will be imparted on the bond, which will result in the instability of a molecule, and that strain is known as angle strain. Angle strain means a strain which is caused by a deviation in the bond angle. So bond angle, or we can say the angle strain, it can be determined by this formula: 1 upon 2 109.5 degree minus bond angle in the planar ring, and bond angle can be further can be calculated by 180 into n minus 2 upon n, where n is the number of carbon atoms. So from these two formula we can easily determine the bond angle and angle strain of any of the cycloalkane compounds. Next postulate was given that the greater the deviation from the normal angle, greater will be the angle strain, and hence greater will be the reactivity of cycloalkane. So this is a relationship between the stability and angle strain. They both are inversely proportional to each other. Means more the deviation from the normal angle, and so more will be the angle strain, and less will be the stability of a molecule. So from this table we can see that the cyclopropane has 3 carbon atom, and therefore its bond angle will be 60 degree, for which can be calculated from the formula. And then angle strain is calculated, which was obtained as plus 24.44 degree. That means plus means that the tetrahedral angle, well, the deviation from the tetrahedral angle is 24.44 degree, means it is less than tetrahedral angle. The deviation is less than tetrahedral, means the internal bond angle of the cyclopropane is 60 degree and the required normal angle is 109.5 degree. So 60 degree is less than 109. So therefore the value which we have obtained of angle strain, it's given in positive plus form. Similarly in cyclopropane also the bond angle is 90 degree, which is less than tetrahedral angle, and so the angle strain obtained will be plus 9.44 degree. As we can see in cyclohexane, you see that its bond angle is 120. It means it is more than tetrahedral. So the more the it will be negative 5.44 degree, means minus means होता है negligible. So here we can say that that is a particular molecule, or which is cyclohexane, it has a angle near about tetrahedral angle. Okay, so that's why they are more stable. Cyclopropane, cyclooctane are similar like this. Next, from this diagram, we can see that first one is of cyclopropane. Here we can see that the bond angle is 60 degree and the tetrahedral angle which is required is given in blue and dots, and it should be 109.5. So the difference will be 49.5 degree. It's a bond angle difference will be there. It can also be seen from this 3D structure of cyclopropane, and in below the structure of a cyclobutane where the bond angle is 90 degree and the difference will be 19.5 degree bond angle. There are certain limitations also of Bayes string theory, which was that it could not explain the formation of a double bond in alkenes. Alkenes, they also have a very large angular strain, and so they will be highly unstable. But we can see that the bonds are also, so it should be difficult for the bond formation in alkenes. The double bond should be formed by difficulty, but practically it is not so. Practically double bonds, they are formed very easily by the dehydration of alcohols or by the dehydrogenation of the alkyl halides. Next limitation of Bayes theory was that due to the large angular strain in as a cycloalkane, which have a carbon atom more than 6, 7, 8, and so on, they should not exist because they are stable, but these rings, they are found to be more stable than cyclopentane ring, and therefore we can say that this theory, it does not explain the stability of the hexane, cycloheptane, all the cycloalkane which contains a carbon atom more than 5. So it is applicable only for the cyclohexanes with carbon atoms 3, 4, and 5. Next story was given by Colson Moffat scientists, and according to them, the cyclopropane has a triangular planar structure with a bond angle of 60 degree, and they are sp3 hybridized orbitals which do not overlap completely, because in cyclopropene the orbitals they are not completely overlapped, as we have seen that in hybridization the s and p orbitals they must overlap completely to form a bond, but here in Colson Moffat, according to Colson Moffat, cyclopropane in cyclopropane, the sp3 orbitals do not overlap completely. Why? This is because of the deviation from the normal tetrahedral angle, because of which the cyclopropane, it shows an angular strain and the torsional strain. Colson also says that in cyclopropane, the rehybridization occurs and bonding between the carbon center exists as bent bonds. So, according to them, the bent bond is formed in a cyclopropane. And now, what is this bent bond? Bent bond means the sp orbitals, they are not completely overlapped, so they get bend, whereas the carbon atoms are bent outwards, and so the such that the interorbital angle formed will be 104 degree, which reduces the bond strain. And therefore, like we as we can see from this slide here, and below is the representation of a bent bond in cyclopropane, where we can see that the bonds s and p orbitals, they do not overlap completely and are shifted outwards. They are shifted outward, they are bent outward, so therefore they are known as bent forms, forming an angle of 104 of to 105 degree. So we can say that these bonds, which bent bonds, they are the intermediates between sigma and pi bond, because they are neither the sigma bonds, neither they are nor they are the pi bonds. So we can say that they are intermediate between sigma and pi bonds, and these bonds are also known as banana bonds. Why is it so? Because they look like a banana in their structure. As we see from this slide here, we can see a banana. When banana is placed in a triangular form, it will look like this. And similarly, the cyclopropane, due to the bent bond, due to the shifting of the bond, or you can say that due to the bending of the bonds outward, it looks like a banana. Therefore, these bonds are also known as banana bonds. This can be further explained from this figure also. As you can see that here the sigma bonds, they are overlapped very well. They are completely overlapped to form a strong bond, whereas in the adjacent figure we can see that the bonds, they do not overlap completely, and so these bonds are the weak bonds and also called as bent bonds. Next theory was given by Sanchez Moore theory. This theory was given to explain the strainless string in a cycloalkane compounds. According to this theory, it was given to explain the stability of the ring with six or more carbon atoms. This theory was proposed for the cycloalkanes with carbon atom more than six. According to this theory, five or less membered rings, they lie in a single plane, but six or more membered lie in a different plane. These rings are non-planar or plucker. That means the way cycloalkanes, cyclopropane, butane, and cyclopentane, these are just planar in structure. That's why they are unstable. Whereas the higher cycloalkane compounds, they are non-planar in nature, due to their pluckered rings. Pluckered means due to the rings, they are shrinked, and therefore the tetrahedral angle, it remains unaltered, and the angle in strain is also zero in such compounds, and therefore these compounds can also be called as a strainless ring, means they do not have any angular strain. Thus, these compounds only exist in two forms, boat and chair forms. So this picture represents the boat and chair form of cyclohexane, where we can see that in boat form, the of cyclohexane, and the chair form of cyclohexane, it has contains six axial and six equatorial hydrogen atoms present in the chair form. So that's all for the this topic, cycloalkane. Thank you.